All right, hello. This is the second video out of 6 to model agricultural runoff in MATLAB. So our first video got us into the background, showed us a case study, talked about what the heck we're doing. And this video is our first introduction into MATLAB itself. So you may or may not be familiar with it. We're going to go through a very basic but very important part of it in order to model differential equations down the line. So variables, we are familiar. If you were to type y is equal to 5 and you hit run, you would get y is equal to 5. And that's helpful. You could hard code equations in MATLAB. You could type y is equal to 2 times 5 and you would get 10. But that's really not helpful in complicated scenarios. That's tedious. Coding is meant to make our lives easier. So we can use something else, such as sims. We hit run. You will see here on the left that x is equal to a 1-by-1 sim. And basically what this does is it creates a dynamic variable and it automatically assigns it to a variable with the same name. So x is equal to x in this case. And the symbolic toolbox is represented in exact rational form, whereas the floating point number returns an integer value. That's the difference between y is equal to 5 and sims x. And it refers to a symbolic variable, like that's what we call it. And you can also assign x to a different function name if you wanted. So we could do f of x is equal to sim x and hit run. And we see here that does the same thing. It creates f of x is equal to x in a 1-by-1 sim. Now, you might have noticed that there is no plural here. If we tried to do that, it wouldn't work. Using input and output arguments simultaneously is not supported. Now, if you're wondering, what's the difference? We can enter sim into our documentation. We can choose the sim or sims function help page, which hopefully is showing up for you. And it says that the sims function, plural, creates a symbolic object that is automatically assigned to a MATLAB variable with the same name. However, the sim, singular function refers to a symbolic object that can be assigned to MATLAB variable with the same name or a different name. So they do slightly different things. And hopping back into our code here, when you assign a number to the MATLAB variable x, the number is represented in like double precision, and then it'll overwrite the previous assignment to a symbolic variable. So if I did x is equal to 1/5 and hit run, x is equal to 0.2, basic math. However, if we were to wonder what the class was, it would be a double, which is not entirely helpful sometimes. So to avoid this, we can do the following. X is equal to sim 1/5, hit run. And then if we hit class of x again, it's now a sim rather than a double. So that allows us to manipulate it within the symbolic toolbox. We'll go ahead and block those out. So we can also create multiple variables, which is important to solve differential equations within MATLAB. You're probably going to have a bunch of variables to work with. And by using sims, we create fresh symbolic variables for interactive symbolic workflows. That is for symbolic variable creation at the MATLAB command line or in MATLAB live scripts. That's a definition for you to remember. So if we wanted to create multiple variables, sim, we would type sims A, B, C. And then we see here on the left, it created 3 new variables for us to work with. If you wanted to create a vector, you could do sims D and then let's see, 1 through 3 and hit run. And that would create D1, D2, and D3 for you. And if you went into the variable D, you would see 1, 2, 3, 1-by-1 sim. You expand that further, it's equal to D1. So it nests them in there for you, which is a little interesting. And then, so this would create a but the very important thing that we're going to get into next would be to solve equations in Symbolic Toolbox. So the very first thing would be a basic example. If we wanted to do if we wanted to model y is equal to a times x squared plus b, which is a very popular equation we're all familiar with, then you would simply type sims x, y, a, b. And if you hit run, it assigns it to that. We're all good. And then as we explore different ODEs, different orders, we can technically, we can differentiate them by hand on paper, but that can get tedious and time consuming very fast, especially if you've taken the class differential equations, you know just how time consuming it is. So instead, make your life easy, use the Symbolic Toolbox to do it for you, which gets extremely convenient. So if we chose a first order ODE. I won't get into the theory behind it, but the ODE equation would be dc dt is equal to negative k times c. So if we wanted to use Symbolic Toolbox to solve the first order ODE, we would do sims c of t over time. This is a first order differential equation with respect to time. So we would do c of t, k, and c0, c naught. And then this is where the new code comes in. We would type equation is equal to differential c of t. Nope. C of t, there we go, is equal to k times c naught, or just c, sorry. And then we would go into your conditions, which is where c naught comes in. You would condition c0 is equal to c0. And then you do c of t equal to c of 0. Oh, nope, sorry, my bad. The solve equation condition. So if we wanted to see what any of this did, we could type in dsolve into the documentation tab, which helps you solve a system of differential equations. For example, it solves the differential equation, which is what I called it. You can name that anything. You can name it equation 1, equation 2, equation x, as long as it's a symbolic equation. And then you would use a diff and 2 equal signs to represent the differential equations. And you would solve a system of differential equations by specifying equation as a vector of those equations. So if you had multiple differential equations to solve at the same time, such as a contaminant decaying into a different contaminant and then that decaying, you could create a vector of equations as long as you named it appropriately, and then you could solve them simultaneously. So if we hit run here, you will see that it returns to you the equation c of t is equal to c0 times exp raised to the k times t power. And that's a pretty familiar equation that you probably have seen before. If we wanted to use symbolic, toolbox to solve the second order ODE, we would do something similar. Let's call it A's time, K1, A0, and then we would type in the same code, changing the variable name. And this would be negative K1 times AT times AT. And then condition is equal to a 0 is equal to a 0. Oh, that's not right, is it? Nope. Yeah, it is. Okay. And then a of t is equal to d solve equation. If we hit run, then it creates for you a new solved equation, which is a of t is equal to -1 over all right, so that should give you a good overview. And you could essentially type any equation right here. You could change this to CO2 injection in a CSTR reactor. And you could do something like AER times CN minus AER times A. And then you would simply just change the variables here. You would change the initial condition here, and you can solve whatever equation you want. So pretty helpful, right? We are going to switch to this. So this is our quiz for presentation. Oh my God, view slideshow. All right, that took me a minute, sorry. So what toolbox must be installed to use this function? How can you create variables in the symbolic toolbox? And what is the difference between using the symbolic toolbox and a floating point number to create a number? What does sims do? And then how would you define f as a symbolic expression equal to 5? Would you use the singular sim or the plural sims? And then lastly, you're going to use the symbolic toolbox to solve the following situation in ODE. So this is our case study problem for the rest of the videos. You're going to see these numbers a lot. So a chemical D is used as a fertilizer on a 27-acre agricultural farm. The BOD runoff was estimated to be 5.3 milligrams per liter, which infiltrates a nearby stream, then entering a pond, which has a volume of 0.2 cubic miles. The reaction is first order, undergoes hydrolysis, and has a rate constant of 0.32 over 32, 1 over day. That will degrade the compound over time. The flow from the stream equals 3 cubic feet per hour, and we assume the water levels in the pond are maintained through equal output flows. And we assume the pond was clean before the runoff occurred. So at t is equal to 0, d is equal to 0. And eventually you'll model this in graphs, but for now you're just going to solve the ODE. So use your background of chemistry to create an equation and use Symbolic Toolbox to solve it. And then the answer key is provided here. And hopefully you got something similar. And that is all. Thank you very much for this video.